how and why solutes are able to dissolve in different solvents. So that language that I use there is very, very important. So we've got the word solute and the word solvent. So solutes usually dissolve into solvents, and together they make a solution. And this language will keep coming up in our definition for what it means for something to dissolve. So the solute is what is going to be dissolving into the solvent. And it's extremely important for us to understand that when you're dissolving something, what's taking place is that the interactions between the solute and the solvent are very strong, right? So if you're trying to make a solution and you've got solutes here, there are solute-solute interactions to begin with, right? So there's all kinds of intermolecular forces that exist between the solute. And on the other hand, you also have these intermolecular forces, these attractions that exist between the solvents as well, right? So there are solvent-solvent interactions, right? So the solute and the solvent are separate at this moment. When you're attempting to make a solution, you have to make it, and it only becomes a solution, it only dissolves if the interactions between the solute and the solvent are stronger than the solvent-solvent and the solute-solute interactions, right? So in order for dissolving to occur, the solvent-solute interactions must be greater than the solvent-solvent interaction and the solute-solute interactions. So you are essentially allowing for this interaction to occur. And when you've got enough strong solute-solvent interactions, that's what allows for dissolving to take place. And we're going to talk about water and why water is such a great solvent. And it has to do with polarity. And we'll make these connections between polarity and intermolecular forces very soon. But you have to remember that water is a polar molecule. So remember from our Lewis structures, this is what water looks like. And because of the difference in electronegativity between the oxygen and the hydrogen, there is a partial negative on the oxygen and a partial positive on the hydrogens. And there's also a dipole present, right? That's facing towards the oxygen. And this all happens due to the difference in electronegativity. But the result of this, the fact that there is a partial negative on the oxygen and a partial positive on the hydrogen, all leads to more interactions, right? When water is a solvent, it is able to form more interactions with all different types of solutes because it is polar. Not only can it interact with other polar molecules, it can also form these interactions with ionic compounds as they break apart into the ions. The second reason why water is such a great solvent has to do with hydrogen bonding. That is a type of intermolecular force that we talked about. It allows for water molecules to have very strong attractions to all kinds of different solvent molecules. So let's take a look at how ionic compounds dissolve. So earlier we learned about dissociation, right? If I've got NaCl, it's going to break apart into water into its ions, Na plus and Cl minus. And when you've got an ionic compound like this, what it looks like, the structure in which it is held is known as a crystal lattice, right? It's held together like this. There are attractions between the positive ions and the negative ions. And when you introduce this crystal lattice into water, into the solvent, what ends up happening is that the water molecules orient themselves based on the different ions that are on the surface. So if you take a look at the surface here, on the very outside of this crystal lattice, you'll notice there's the green Cl minus ions and the purple Na plus ions. And depending on which ion the water is close to, it will orient itself such that there is an attraction, right? Notice the partial positives that are on the hydrogen and the partial negatives, that's on the oxygen. Because the green is Cl minus, the hydrogen that has the partial positive is facing towards it. There's an attraction between those two. And if you take a look at the purple with the sodium ions, the water is orienting itself such that the oxygen is facing it, because that's where the partial negative is closest, right? So once that is oriented, once that water arranges itself like that, it allows for that water, those water molecules to bring apart or pull those ions because of that interaction, right? So it's going to cause for these ions to move away and for water to completely surround it. And this, when this ion, this particular Cl ion, moves away, then it allows for more water molecules to come close to the ions that are towards the inside of that crystal lattice, right? And eventually, what you want, you'll end up with a situation where all of the ions are surrounded by water. And be very careful in noticing the structure or the way in which the water is oriented. The white, which is the hydrogen, the partially positive, surrounds the Cl minus, or it faces in a way that the white is closest to the Cl minus. And for the Na plus, that the red, that the negative, the oxygen, the partial negative, is facing closest to the Na plus. So that attraction allows for a layer of water molecules to be surrounding each ion. And when there's that much water surrounding each ion, it stops these two from attracting each other, right? This Cl ion cannot attract this Na plus ion because it's surrounded by water. And when that happens to all of these ions, that's a process called hydration. That's when water surrounds each of those ions in a way that they cannot attract with the other ions anymore. And that at that point, we can consider something to be dissolved. Okay, that's pretty much it for that video.